we need to then talk about, right, here's our solution that we just came up with. We wrote that out. Let's go through the steps for solving this now. Okay, so the first step for separation of variables, step 1, is we need to check that our problem meets the requirements to solve a separation of variables type problem. So check that problem meets requirements for SOV, separation of variables. All right, what are those requirements? Well, there's 4 basic requirements that you have to meet. So first requirement is the PDE, the partial differential equation, and all BCs, all boundary conditions must be linear. Linear, okay? Again, what does linear mean? It means you can't have a product of 2 variables or derivatives of those variables multiplying each other. So here we see, okay, we have a second differential plus a second differential in our PDE. That's fine. Right? Second differential is not the same thing as, like, say I've got dt dx times dy dx, right? Those would be nonlinear. Here it's just a derivative, second derivative, or whatever. That's linear. That's okay. Okay, and then the boundary conditions are these all linear? We have just temperature is equal to 0. That's okay. We have just a derivative is equal to 0. That's okay, right? These are all linear, so we're check on that, right? We're okay with that one. Okay, second is the computational domain. Computational domain must be simple. What does that mean? Let's just scroll back up here real quick. So the computational domain in this has what? It has the boundaries of the domain are at x equals a constant value and y equals a constant value, whether 0 or L or H in this problem. So a simple domain just means that the domain falls along constant values of the variables. Right. So a rectangle, or in the case of a cylindrical geometry, it would be like a cylindrical shell. You can't have like a tapered geometry or anything. That won't work. Okay. C is what? The PDE must be homogeneous. Do we have a homogeneous PDE here? This guy. Yes, we do. So if you had generation or you had like the extended surface type situation, you can't use separation of variables. It's not homogeneous. Last one is both boundary conditions. This is an important one. So both boundary conditions in one direction must be homogeneous. Okay? Think about what that means. So I have to look at, okay, the x direction or the y direction, and in one of those 2 directions, both the boundary conditions have to be homogeneous equations. What is a homogeneous equation? It's when temperature, in this case, or its derivatives are equal to 0. Right? There's nothing on the right-hand side that's a constant or a function of x or y. So let's look here. We have, let's see, let's look first in the x direction. So here we have temperature is equal to 0, and we have derivative of temperature is equal to 0. Okay, so check. At least in the x direction, we know it's homogeneous. Both the boundary conditions are homogeneous. Okay, in the y direction, we have derivative equals 0, and then we have temperature equals a temperature that is not homogeneous. So we're homogeneous in x, but not in y. That's okay, we can deal with that. We just have to have at least one direction. Okay. Incidentally, like if we had a situation where like this boundary condition, the y ones, you can still actually make those homogeneous. We just have to substitute and say, all right, instead of using temperature, we're going to use theta, and theta is equal to the difference between the 2 temperatures or something like that. So you can make substitutions, or there's some transforms you can do to make it homogeneous. But as it stands, this is not a homogeneous setup. Okay. So we go through and we satisfy all these requirements. And why are we having these kind of weird requirements? Well, basically what we're going to try to do is we're going to break the problem into a function of x and a function of y, multiply those two things together, and then solve for independently the function of x and y, like come up with expressions for that function, the functions separately. Okay, so in order for that approach to be valid, these conditions have to be met. Okay, so we'll see where I'm going with this. All right, so moving on to the next slide here. So the step 2 is separate the variables. I guess I already wrote it out. So separate the variables. So what does that mean? Well, we're gonna assume right now we have a function of temperature, or temperature is a function of both x and y, right? We agreed that the temperature can't be approximated as 1D. It truly is a 2D function here. So we're going to make the assumption, based on the things that the criteria we just satisfied, that we can separate this out into two things: a function of x and a function of y. Right? We'll call that function of x tx, and we'll call the function of y ty. But think about what I'm saying. I'm saying there's a function, a group of terms that are only a function of x. And there's another group of terms that are only a function of y. We can multiply those two things together and come up with our combined solution. That's fundamentally what we're saying here. So don't lose track of that as we're going through. That's kind of the foundational thing. We're assuming we can get to a solution that looks like that based on the criteria that we set up. So now, okay, this is what we're assuming. We're going to take this and substitute this into our PDE up here. So let's do that. So we're going to substitute in. So we have d squared dx squared of this thing here, which is, we'll shorthand call it tx times ty, right? Sort of shorthand that down, plus d squared dy squared of the same thing, tx ty, that equals 0. So, okay, I'm taking the partial derivative in the first term, the partial derivative with respect to x, and I have tx times ty. Now, tx is a function of x, right? Ty is not a function of x. So if I take the partial derivative of something that's not a function of that, the thing you're taking the derivative with respect to, it just comes out, right? It's sort of, you can take it out of the front of the equation. So this becomes ty times partial of tx plus tx times partial ty equals 0. Clear ty. Does that make sense? So you're taking the partial so you can pull that function out, right? It's not affected by that partial derivative. Okay, so next step would be, we're trying to get all the y stuff on one side and all the x stuff on the other side. So let's go ahead and divide through this whole thing by tx times ty. Okay, so we'll divide through everything by that, and then we end up with, on the left-hand side, stuff that's just a function of x. So now we'd write d, no longer just the partial, right? So d squared tx over x squared divided by tx, right, that function, plus d squared ty, oops, y, I said dx, dy squared over ty equals 0. Right? Okay, so we've now successfully separated where we have this term here is just a function of x. This term here is just a function of y. All right, so great. So this is progress. Maybe it's not clear yet how it's progress, but we've at least separated things out, and we can start to come up with separate solutions for tx and ty. All right, so what's the next step here? We need to recognize something about how these two terms are related to each other. Right, so the terms are related to each other. If you kind of look at it, so let's say, right, this is only a function of x. So what happens if I change the value of x, right? If I say pick a value of x and allow that to change, how does this term change? Well, this term changes, right? It's a function of x. It's a very circular way of saying it. It's a function of x, so it must change. This term is only a function of y, so it will not change. So stop and think about that. So if you have these two separate things, the only way they can be related to each other is if they're both equal to a constant. Okay, make sure you can see that, right? If I change x, the other one doesn't change. The only way that can be true is if they're both equal to a constant. Okay, so that is saying my function of x is going to be equal to, right, we bring over this thing on the right-hand side is minus the function of y, and those are both equal to some constant value, right? F of x is equals minus f of y equals some constant. Right? That just has to be true based on that statement down there. Right, so my function of x, we'll write it out, is equal to d squared tx over dx squared over tx. Right, that's going to be equal to, we'll call this constant lambda squared, right? So lambda, we'll call lambda squared because we want lambda to be, or we want the constant to be unambiguously a positive value, right? And then f of y here is just the same thing, d squared ty dy squared over ty, and that has to be also lambda squared, but these have to be opposite signs, right? And we don't actually know which one is going to be plus and which one's going to be minus. We just know that they have to be opposite signs. So we would write, okay, this one can be plus or minus up here. This one then has to be the opposite side, so it'd be minus or plus. Okay, so we'll just write it kind of flipped around. All right, so we got these now two functions. They're both equal to a constant. The constant has to be unambiguously positive, but we don't know which sign goes in front of which one. But this should be encouraging, right? Now we look at it, we have an ODE for f of x, we have an ODE for f of y, and now we should be able to solve both of these using our conventional techniques and then come back and put them back together, right? So this is now actually progress. So the next step then is to think about, okay, I've got this plus or minus, minus or plus. I need to resolve that. I need to figure out which of these two constants is positive and which of them is negative. All right, so the rule here is we want to choose, we want to choose the positive constant for the direction that has the homogeneous boundary conditions. Okay, so in this case, we want the following. So we want it to look like, we'll bring this over and just write it this way. So d squared tx dx squared. This is going to be, we want it, let's write it this way, positive lambda squared tx equals 0. Okay, so I may have said that back, but this is what we want. We want to get to, x is our homogeneous direction because it has homogeneous boundary conditions, right? So we want to get to an equation where we have d squared tx plus dx squared plus lambda squared tx equals 0. So that's the equation we want for our homogeneous direction. Okay, and then that leaves d squared ty dy squared minus lambda squared ty equals 0. So this is our homogeneous boundary conditions direction.